We did our project on the maths behind LIDAR.
So what exactly is LIDAR? Standing for light detection and ranging. It's an imaging system similar to radar and sonar, but instead of radio or sound waves, it uses light in the visible or in the infrared, visible, and UV spectrum. It's made up of three parts: receiver, emitter, and mirror. Essentially, the receiver sends out a laser, which bounces off the mirror, which is rotating, which hits the object, is reflected, and then hits back to the mirror. Some real-life applications of this is used in automated vehicles, like self-driving cars. It's used a lot in 3D modeling, especially in natural geography, like landscapes and mountains, but also for interior mapping, specifically for archaeologists who need to access inaccessible places and dangerous digs. It's also used in pollution monitoring, as you can see in the bottom right corner. That's a crop sprayer, which is spraying pesticides, and it can detect fine particles at pretty high heights. And so here we have a demo of Rishi using a LiDAR. We're using a 2D LiDAR, and essentially Rishi is moving a whiteboard up and back and forth, and also to the sides. And you can see how LiDAR is actually detecting the 2D position of the whiteboard. So the LiDAR gives us a bunch of points, but it gives us each point has three things in it. So the first is the angle. And so the angle is given, if you remember this term, bearing, so due north. So we need to convert it by taking 90 minus theta. The second is distance. But we don't actually know, the distance is without a unit. So Rishi found by himself that 300 of these units is equal to 1 foot. Rishi was moving the whiteboard in front of the LiDAR a lot, but the LiDAR is usually the one that's moving. So we need something called state estimation, which is essentially saying, the LiDAR needs to know where it is at all times. So whenever it moves like an angle or is transformed at all, it knows exactly like where it's moving. So at any given time, it knows its precise location in relation to its surroundings.
Before we can know where we are at any one point in time, we need to have a way to keep track of our location. And the way the LiDAR does it sees the difference between its previous surroundings and its new surrounding. And each time between those two differences, it's able to extrapolate two main key pieces of information. And that is the transformation and the rotation. And it's essentially saying, how do I get from this set of points to these set of points? And one critical point in how it's able to do that is that all the points are one-to-one correspondence. Before we can go ahead and start solving the point set registration problem to find our rotation and our transformation, we need to make sure that our data is manageable and readable. You can only perform geometric matrix operations with Cartesian coordinates, converted the raw bearing coordinates to polar coordinates by doing 90 minus theta. Then we converted these Cartesian coordinates, which is simply r cos theta, r sin theta. And finally, we go ahead and place it into a matrix. One matrix before the pre-image, let's call that state A, and one for the post-image, state B. These are one-to-one correspondence to points on point 1, point 1. Is keep at 0 because you have a 2D LiDAR, but the x and y are simply r cos theta, r sin theta. Another thing to keep in mind is that each point can also be considered as a vector between the LiDAR and the object itself. And this will be important in our calculations that we will be showing right now. We need to calculate the centroid because the information from the LiDAR, if we kept the LiDAR at the center, it doesn't make much sense because the LiDAR is always moving. And the centroid can be computed by simply adding up all the points and taking their average. And we find one centroid for the visible and one by the effective miles the image. See, how did it go from the previous image to the next image? Transition or the translation matrix. And the way how it's calculated is that we look at all the points inside both matrices A and B. Let's take point A, for example. We subtract for the centroid, and that's and that's a legal operation because of when you take the negative, if you get the point and tail, you're able to add those up and you get this vector. And then we multiply them because we're essentially going from one to the other. The reason we're taking the transpose is because we want to keep the x, y, z consistent. And again, we need to take the average of all of this in order to normalize the entire data set. Now that we know how we went from, now we have a general matrix W, which tells us how did we go from our pre-image to our post-image. We now need to actually process matrix W. And one way we do that is a singular value decomposition. That breaks it up into two unitary matrices, matrix U and matrix VT. And when we multiply these together, we are able to get the rotation. And we can ignore the scalar component and simply replace it for the identity because the transformation is a fixed point translation. And the reason we take the determinants U and V, I'll gloss over it in the presentation. It's simply to avoid the reflection. I talk about this more in my paper. And finally, we are able to extract the translation because we know the rotation. We calculated CSS prime. We multiply it by our after data set, and we subtract it from our original, and that's our translation matrix. Thank you.